Okay, we want to sketch three graphs. They're all graphs of transformed log base 2 functions. So you probably want to start with a graph for the y equals 2 to the x function. You got your usual values. And log 2 function is going to invert column. The x's become the y's, and the y's become the x's. Which gives you the graph of the base 2 log. And I constructed this many times, and I know you can construct it. You're all pretty good at this, if you just remember to do it. Okay. So the big point here is you get this graph. Then it's a fairly simple matter. Well, let's leave this aside for a minute, okay? So this involves a horizontal compression by a factor of 3. Means all the points move 3 times closer to the y-axis. And that's the transformation we haven't talked a whole lot about. We can follow here. So the second transformation. Oh, you're doing x plus y. Okay, so let's do log base 2 of, don't have a lot of here. I can, yes, okay, so let's do log base 2 of x plus 3. What happens if you replace x by x plus 3? You shift it 3 units to the left. I kind of abbreviated that, didn't write it real carefully. Yeah, I say you shift -3 in the horizontal direction. And that means every point moves over 3 units. So this point where x equals 4 has to move over here where x equals 1. This point where x equals 2 has to move over to where x equals -1. This point where x equals 1 has to move over to x equals -2. And this point moves over, and this point moves over, and you can figure out what the coordinates are. Right there is your graph. And the y-axis moves over here. Vertical asymptote is going to be y equals, sorry, x equals -3. Okay, the y-axis x equals 0. If all your x's shift 3 units in the negative direction, your vertical asymptote becomes x equals -3. And I curved that a little too much. That's going to x equals 2, but it doesn't. Okay, so that's all it takes. Draw your graph, shift every point 3 units to the left. What do you do here? Well, you take your log base 2x graph and move it up 3 units. Or b units. So let's say that b was, we don't want it to be too big. I'm just going to do b equals 1. you shift plus 1 unit vertical. Well, that means 1 unit is this far. Okay, so like this point moves up 1 unit. This point moves up 1 unit. And this is 1 unit. This point moves up 1 unit. This point moves up 1 unit. This point moves up 1 unit. And this point moves up 1 unit. You get these points. The graph is going to look something like this. It's going to be 1 unit higher in this graph, in the original graph, at any point. And now the log base 2 of 3x, probably don't want to draw that on the same graph, so let me quickly sketch another graph. I'm actually going to extend the x-axis out of it. -2 down here. It's hard to read that -2. So here's the graph. Log base 2 of 3x, horizontally compressed by a factor of 3. Every point moves 3 units closer to the y-axis. So if we're 4, 3 times closer to the y-axis is at 4/3, which is 1/3. So 4 becomes 4/3. This point is over here. Two, or if x equals 2, and you're horizontally compressed by a factor of 3, you go to 2/3. So 2/3 might be about here. So we'll say that this is where x equals 2/3. This point will move here. Okay, x equals 1 goes to 1/3. I'm not going to mark that, but that goes over here. And this point gets 3 times closer to the axis, and this point gets 3 times closer to the axis. And you end up with the log graph. It's quite a bit steeper. Okay. Now, another way to see this, you understand this great. If not, probably won't cost you much. It might get a little extra boost. Okay, well, log base 2 of 3x is log base 2 of x plus a log base 2 of 3. And that means that every point moves up. Distance equal to log base 2 of 3. Okay. And log base 2 of 3 is about 1.6. 1 second. Actually, it's more in the neighborhood of 1.5. No, it's a little more. It's close to 1.6. Between 1.5 and 1.6. So you move every point up 1.6 units, and you get to the point of this graph. Okay. a little hard to draw that. I'm not gonna try. Just gonna say we can actually do that, okay? Okay, well, there are many other things you can do with graphs of logarithmic functions. I'll tell you that some of the questions on the homework relied a little more on technology than I prefer to do. So if I ask you to do anything with log graphs, it's mostly going to be transformations. Okay, now you did have questions, some of you had questions about natural logs. What's a natural log? Somebody want to tell me what the definition? Okay, so somebody told me, and I think everybody pretty much knows, you're doing real well here. This is log basic. Natural log is log basic. So if we wanted to do a graph of the natural log, if there's a table with exact values, and then and there's an epidemic of carelessness that's centered on me. Okay. This should be y equals e to the x, not y equals natural log of x. Okay. This is going to be y equals natural log of x, which is log base e. Here's y equals e to the x. The log base e is just going to reverse the columns of the e to the x function. And you're going to get okay. Now, the question is, what does this look like? Well, what's the value of e? Anybody tell me approximately what the value of e is, or maybe two integers that e lies between? Okay, so e is between 2 and 3. Closer to 3. So that I'm going to go through the point 1, 0. Every exponential function does. Okay. If x e y is 1. Well, here's 1. So here's 2. And here's 3. And here is e. You can use your calculator to calculate e squared or e cubed. Now, I didn't leave myself room to do e cubed because that's going to be a little more than 7. Okay. E squared is going to be a little more than 7. So it's going to be out here a ways, so we're not going to be able to put it on this graph, but it's just a number. I'm going to say, just for the sake of just graphing the function on these, on this domain, we can say e is about 2.7. E squared is then going to be about 7.29. A little more than that, 7.3. I don't remember what I hadn't thought about it in a while. And A cubed is out somewhere close to 20. Okay, so if you're doing so 1 over E is going to be between 1/2 and 1/3. It's going to be a little less than 1/2. So here is like one over E. Then 1 over E squared is going to be a little more than 1/3 of that. So you're going to have points down here. You're going to have a point out here. It looks like this. It looks a whole lot like your regular log function, except it's a little flatter. Let's make sure we understand this in context. I'm not going to go through the details of graphing. And I think we've done this already, but I'm going to put A here. I shouldn't put this point here. So I it's a little high. Here's 4, here's 2, and so forth. If I want to graph y equals 2 to the x, well, you know, from long experience, how to graph y equals 2 to the x. Want to graph y equals 3 to the x? Well, you're going to have a point here at 3. And 3 squared is 9, so you're going to have a point up about here. You're going to go through the origin. You're going to be a little lower than these points. Here's y equals 3 to the x. If you want y equals e to the x, well, it's sandwiched in between these two. Now over here, it's kind of hard to tell where it is, but here it comes up. And here you can understand that y equals e to the x. It's closer to 3 to the x than it is to 2 to the x, because e is closer to 3 than it is to 2. I didn't write it down up here, about 2.7. Okay. So there's e to the x. Now, if I want to graph the inverse function, very well, easy to see that this might be 2 to natural log of 2. Sorry. Log base 2 of x here. And log base 3 of x. Be like here, not drawing this very well. And log base e to the x should be in here somewhere. We can draw a more careful graph. But there it is. If you invert these graphs carefully, you're going to get a pretty good approximation of the e to the x graph. Okay. And I might actually ask you to do this. Just show me the 2 to the x graph, show me the 3 to the x graph, show me your best estimate of where the e to the x graph would be without having to do a lot of calculations. And then show me the inverse functions. I did a bad job with the inverse functions. I don't take this literally. you can visualize what this looks like if you flip it over. So, okay. That's what you really want to know about log base E. Now, there's a lot that it'd be really good if you knew about the number E. And I'm going to try to find time to clarify that for you. Maybe today, maybe another time. Let's go ahead and move on to something that hopefully is going to be a little easier than what we've been doing up to this point, because I kind of promised that. Okay. There's been two equations and two unknowns. If you graph the system, easy to graph it by intercepts. The x-intercept of this one is going to be 11.5. That's about 5.5. So let's go ahead and just graph out to x equals 5. 5.5 will be about here. And I'm not going to write this out. Everybody knows how to do this, or you did at one point, and all you got to do is a little bit of review. Y-intercept occurs when x equals 0. That's going to be y equals 11/7, which is a little over negative 1.5. So let's go ahead, scale this, and we see that the y-intercept here is going to be along with that. That's one part of the chart. This is kind of a bad line, but here we have. This is 2x plus 7y equals 11. Every point on this line, if the line is exactly drawn, is a solution to this equation. And every solution to this equation, every pair of numbers x and y, satisfy this equation, have to lie along this line. Excuse me. This line has an x-intercept of y equals 0 at 9/4, which is 2.5. So, part by 4 scale there, occurs maybe about here. And the y-intercept when x equals 0, that's at y equals -3. So that might be about here. So to the extent I drew these lines correctly and had an equal scale, the point where they cross should be close to a solution to the equation. So I'm going to estimate the coordinates at this point. XY point approximately equals, looks like about 3.5, which I'll write as 7.5. And somewhat less than 1, I'm going to say about 2/3. And I'm going to just ballpark 2/3, 0.66 repeating, but I'm just going to round it up to 0.7 because it's not a very precise graph. Okay, if I plug 3.5 in for x, I'm going to get 7 here. If I plug in 0.7 for y, I'm going to get 4.9, which is going to give me 11.9 up here. If I plug in 3.5 here, I'm going to get 14 minus 2.1, which is like it's 11.9. Now it's 10.9. Okay. So it's a little high. Okay. So this isn't a great approximation to the solution. Okay, well, we did this in an assignment quite a while ago. That's a quick review. All I got to do is know how to graph a linear function. And you can do the same thing I did, probably more precisely, because you might be more careful. Okay, now that's the geometric interpretation. How do we solve these equations? Well, I'm going to write these equations out. So Okay, here are the equations. I'm going to call this equation number one. I'm going to call this equation number two. I noticed that if I multiply the first equation by -2 and add it to the second, I'm going to have a -4x and a 4x, right? Which means my x's are going to go away. So if I do -2 times the first equation, I'm going to have -4x minus 14y equals -22. And if the second equation remains unchanged, I get this. If I add these two equations, -4x and 4x gives me 0. -14y and -3y gives me -17y. Yeah, okay. I thought I had. Okay, anyhow, -22 and 9 gives me -13. So y equals -13 over -17, which of course is 13 over 17. And that's approximately 0.7. Meaning that my 0.7 here just happened to be pretty close to the proper solution. Well, if I take now this solution and plug it in here, I get the equation -4x minus 14 times 13/17 equals -22. I've got a denominator here, so I get to multiply everything by 17. And of course, I want to multiply both sides by 17. And I get this. Okay. 14 times 13 is 182. See, that's 10. That's 42. Yeah. Seventeen times 22 ought to be easy. It's 340 plus 34 is 374 negative. Okay, so at this point, it's totally obvious that x is going to come out pretty close to 3.5, right? Just visualizing the well, no, numbers are too good. We get -68x. And of course, I'm going to add 182 to both sides. Okay, working memory here. Get -100 and 188, I think. No, 192. So we get actually equals 192 over 68. If I did my arithmetic correctly, I don't think it's far off. It might well be off a little bit. Double that, I get 136, leaves me to, so I'm getting somewhere around 2.7. Could be off by a tenth, maybe even more. So we get x equal approximately equal to 2.7. Left approximate solution. 2.7.7. I plug these numbers back into both equations. 2.7 times 2 is 5.4, and that's 4.9, and 5.4 and 4.9 doesn't add up to 11. Adds up to 10.3. 11.3. Now it's 10.3. So that didn't work out real well. So there's something wrong with my arithmetic, but do you understand the point? Okay, the point is simply that if I multiply one or more equations by the right number, I can eliminate a variable and solve for the other one, which I then plug back into one of my original equations. And I probably should have plugged that back into one of the original equations. Numbers would have been a little smaller, and I get a solution. If I make an arithmetic error, well, I make an arithmetic error. Don't really see what the error is. Pretty sure there is one. I think we've got a volunteer here. Okay, well, I shouldn't have been off by that much. There's a superstition out there that this is closer to 0.76. This is closer to 2.8, actually like 2.82. So let's go ahead. Okay, if I double that, I get 5.64. 0.76 times 7 is 4.9, 5.32. Okay, and what did I say that was? 5.32, about 5.3, and 5.6. Yeah, that comes out real close to 11. Okay, I bet this works too. 4 times that, I'm going to give you that multiplication. It's going to be 12 minus. It's going to be a little less than 11, and that's going to be a little more than 2. 11 minus 2 gives us 9, but I'm coming out with less than 9 because of those approximations. Anyhow, you plug the numbers in right, and your brain is working, or maybe your calculator, I think works out. Okay. And if you plug in the exact fractions, if I do these exact fractions, do it all exactly, and that should be exact, that should be exact. So if you plug them in, you're going to get it. Now, the point is not the arithmetic. The arithmetic is just the arithmetic, and everybody can do the arithmetic. Now, if you ended up with this and didn't think to multiply by 17, the arithmetic would be a bit nasty. I mean, the numbers are a little bit big, but you're not dealing with a fraction. You multiply through by 17, you clear the fraction. Remember that basic principle of the equation is if you got denominators, you clear them. Okay. That's going to be important for rational expressions and so forth, as you know. Okay. Well, all that aside, it's a pretty simple process in this case. We just figure out what to multiply both equations by. In this case, we only had to multiply one equation by another. And you eliminate a variable. So I'm going to give you a problem to do. I'll just write it small down here now. Okay, just write that out for your number. Figure out what it takes to solve it. Okay, now go ahead and start a problem using these numbers. Okay. Now here's my equations. Now, when you do this, I want you to do it in the form that I'm using here. There's a reason for that. People in the support course learned a little bit about the reason. Okay. It's real easy to get confused, and also we're going to adapt this to matrix techniques. And if you do it in the form that I'm indicating here, it's going to make that adaptation much easier for you. It's not difficult. Keep it in the same form. So my form is, I keep my x's lined up and my y's lined up, and my equal signs lined up, and those numbers on the other side of the equal signs lined up. Okay. Then I write up what I do to each equation. I document the fact that I multiply this equation by -5 and this by 7. So gives me these two equations. It's easy. If I did the numbers right, it'll work. Okay, then I add the two equations. And I get 24x equals 56. And I solve, and we get x equals 56 over 4. Which vertically reduces now to 19. And of course, we can reduce the fraction. It makes it easier. You just deal with smaller numbers. Okay. I think everybody understands exactly what I did here because everybody pretty much did that. Then, got this. You take this. I just substitute it for x. So, substitute it for x. And now this equation gives me 5x minus 7y equals 14, where replace x by 19/6. I solve the equation for y. First, I multiply both sides by 6. I can do 6 times this, 6 times this, 6 times this, and that clears my fraction. And I get 95 minus 42y equals 84. So not that big. So I get -42 y equals 84 minus 95, that's -11. So y is 11 over 42. Now I can take both of these numbers and plug them into the second equation. I plug them into the second equation because I plug my solution for x into the first equation. So even if this number is wrong, if you solve this right, it's going to give you a number y that makes the first equation true. But it doesn't necessarily make the second equation true. If you solved it right, it will. So we plug these numbers back into the second equation. Okay, plug that into the second original equation. And I'm not going to actually do that. But you plug it into here and see if it works. I'll kind of do it in my head. 19.6, just approximating, because that's a little more than 3. That's about 1/4. Okay. That's all right for the first equation. The second equation, I'm getting a little more than 18. So maybe I made a mistake somewhere. Okay. So if I made a mistake somewhere, I go back and check my work and see what I might have done wrong. Couldn't possibly have done anything wrong. That's too simple. It's 95, that's 42, that's 84, that's 92. I get this right, that's 24x. And let's see, 18 times 70 plus 56, that's 46. That's negative 70. 6 over 24 is, it's 14 over 6. See, by checking, I found an error that I pretended to make. And I can correct that. Oh, man. Did a good set of squats the other day, and I'm still enjoying the benefits. Okay, 14 over 6. So that 19 should be a 14. So that 95 should be a 70. Negative 11 ought to be a plus 14. So now I get 14 over 42. It's not a whole lot better, but yeah. Oh, second time's easier. Do 3 more times and feel okay. Okay, let's see. So I plug that in. 14.6 is like 2 1/3. Going to give you like 14.16 or something like that. And still not working real well. Anyhow, that's a process. And you want to follow that process. You should find this assignment pretty easy, but do it in a systematic manner. Try to do it the way I've set it up, okay? Because when we do 3 equations and 3 unknowns, if you don't set it up right, it's not going to translate over to the matrix. And if you do it right, then the translation is very easy. Okay, let me have your quizzes.